random matrix theory as such is like a vast topic in itself, worth a 1 or 2 semester course in itself. So to compress it all down to 1 or 2 lectures is not doing justice to it, and also not quite easy to do that. So what I am going to do is to confine myself to applications of random matrix theory in the context of complex networks. That is one thing. So that somehow brings down various things that we need to do, and also to appreciate what this beast random matrix theory is. I'll do some simple calculations to show like scratching the surface, like what kind of calculations goes into it. But certainly the mathematics behind it is somewhat harder and kind of not easy to catch up in 1 hour lecture. But if some of you are kind of interested in it, you should go back and read the textbooks on random matrix theory. And so clearly in this set of 2 lectures, we are going to deal with matrices. There are 2 kinds of matrices that I am going to deal with in the context of complex networks again. So one is what we call the adjacency matrix, and other is what's called the Laplacian matrix. And the whole of what we are going to do is all about the spectra of these matrices, meaning that we are going to be working with the eigenvalues and the eigenvectors of these matrices. So that's what the plan is. So in general, the way I'm going to proceed is initially, maybe for 20-25 minutes, talk about one single eigenvalue, which is very useful for many purposes in complex systems, especially in networks, which is the largest eigenvalue of these, whether the largest or the smallest. And then look at what is called the bulk of the spectrum. So in other words, if let's say one of these matrices is an n by n matrix, you have n eigenvalues. So often what is very important for most applications, be able to figure out what's going on in your network is either the first or the second eigenvalue. But rest of the bulk of the, say, n-1 or n-2 eigenvalues, they carry lots of other information about interactions, what is in general, how is the information organized inside your network, and so on. So that is where the random matrix theory comes from. So I'll first deal with the principal eigenvalues, and then we'll go into the random matrix part, and finally a small bit about the eigenvectors. So this is what we will cover in the 2 hours that we have today. Okay, so this adjacency matrix is Aij is equal to 1 or 0 depending on whether the node I and j is connected or not. Okay, by now you probably know about that, and this matrix L is D minus A. A is the adjacency matrix and D is the diagonal matrix. Diagonal matrix whose elements are all the degree of the ith node. So it will be something like D1, D2, Dn. So most of the time I am going to assume that these matrix are of order n by n or order n. This capital N. So which means there will be D entries along the diagonal and 0 everywhere else. Yeah, so it will be either symmetric or non-symmetric depending on the context. Yeah, so it should be 1 or 0. So as he already said, this adjacency matrix would either be a symmetric matrix if it's an undirected network, or it will be a asymmetric matrix if it is directed network. So the object of interest is something like this. AU is lambda u. These are the eigenvectors and these are the eigenvalues. And by now all of you would know that if A is a n by n matrix, there will be n eigenvalues and n eigenvectors. Each eigenvalue will carry its own eigenvector, and for those I mean we are going to deal with these objects all the time. So, I am not going to run a course on linear algebra, but nevertheless you can think of it as like finding eigenvalues is equivalent to rotating your basis. Okay. So, if you had something like, let us say, a standard basis and let us say 2 points, let us say a point here, it has no component on the y direction. So, you might want to write it as 1 0, or if you had a point here, you will write it as 0 1 because it has no component along this. But on the other hand, if let us say you have a point here, maybe somewhere here, in that case you can actually rotate your axis to make this axis coincide like this. And when you do that, you will manufacture a new eigenvector which will be something like this. And now right now the way it stands, if you describe it in terms of these two bases, it will have both the components. So, it will have something like x1 x2, but once you kind of coincide like this, then it will once again go back to this in the new rotated basis. Okay. So, all of finding eigenvalues and eigenvectors is about geometrically thinking, essentially this rotating your basis. So, you have a collection of numbers, rotate the basis in a clever way such that you can describe it instead of like this in terms of something like this. So, your eigenvalue will be like the length of your this distance in a sense. Okay. So, similarly you can also write an equation for eigenvalues. So, typically if it is a symmetric matrix, this is the only thing that is possible, but if it is not symmetric, you can have a left and a right eigenvector. So, the goal of spectral graph theory is simply to be able to analyze these quantities lambdas and u's and extract as much information possible, as much information about your network as you can. So, you may want to know about the static structural properties of the network or extract even dynamical properties, in the sense of if some dynamics is running on the network, could be coupled oscillators to all kinds of other things. What more can you say about examining these eigenvalues and eigenvectors? Okay. And so, if you have, let us say, this matrix, adjacency matrix A, you will have eigenvalues which are like lambda 1, lambda 2 up to lambda n. If you had this matrix L, the Laplacian matrix, you will have mu 1, mu 2 up to mu n, and this is equal to 0. So, the elements, sorry, the eigenvalues of the Laplacian matrix defined this way are guaranteed to be greater than 0. Okay, it is positive definite, and these numbers lambda 1s are guaranteed to be real provided it is a symmetric matrix. If A is a symmetric matrix, these numbers will be real. So, you will be dealing with the n real numbers, not complex numbers. So, if A is a asymmetric matrix, like as it happens for a directed network, then these numbers are in general complex, but these are always guaranteed to be real and positive. Okay. So, first, as I said, we will work with the principal eigenvalues. So, I will give you a few examples of what happens. Maybe let me write down a few properties. So, if I had something like this, L, I had already used U there. So, this is the eigenvalue equation for the Laplacian matrix. So you can see that the smallest eigenvalue of Laplacian is always guaranteed to be a 0. Okay. So mu. So in this, in the way I have written, mu n is the smallest eigenvalue. I could have started from n and made mu 1 the smallest eigenvalue. It does not matter, but this mu n is guaranteed to be 0, and the corresponding eigenvector is just ones. All the elements are 1. Okay. This is very easy to see. I want to save time, so I will not do the proof, but you can check this yourself just from this definition of L. All you need to do is, so you are asking the question, D minus A, D and A are matrices acting on V, gives you 0 times V. Either you take one of these, it can be proved in general, but if you want to like reduce your job to see how this comes about, you can call this as mu, take V to be a column matrix like this, which will be, there will be n elements, put them here, you can show that mu is 0 in that case. Okay.
D is what again?
D is a diagonal matrix where the entries are all the degrees of the nodes. So D1 is the degree of first node and so on. So in other words, the fact that you have the eigenvector to be like this basically means that the eigenvalue 0 tells you something that's common about all the nodes on the network. Okay. So you compute the Laplacian, examine the first eigenvalue, it's guaranteed to tell you something common about all the this one. The second smallest eigenvalue, which will be mu n minus 1 here, so in this notation it will be mu n minus 1. It will tell you about the connectivity of the graph. So it will tell you about the connectivity of the graph that you are examining. So let us say for example that this number is a small positive number. Okay. If it is a small positive number, it means probably that you have two kind of communities in your graph, okay, which are nearly disconnected. There may just be a few connections between them. So in general, this is a measure of the connectivity in your graph. Okay, I will skip the part about minimizing this, and okay, the third one that is of interest to us is what is called the spectral radius, which is a more fancy term for simply the largest eigenvalue in magnitude. Okay. So if so now I go back to this adjacency matrix A, and rho of A, which is the spectral radius, is simply the maxima of this set of eigenvalues. So in general, if these eigenvalues are complex numbers, then you take the modulus of them. And the largest, the eigenvector corresponding to the largest one is called the principal eigenvector. let us say that maxima is actually lambda 1, then it is the eigenvector corresponding to lambda 1. And this eigenvector is very important in many applications ranging from lots of stochastic processes. In particular, for instance, one place where it is supremely important is in this PageRank algorithm, which powers many of the search engines that we have today. So, the eigenvector components corresponding to this eigenvalue gives you the ranking of the web pages. So, it is a separate topic in itself, but nevertheless just letting you know that it is important. Yeah. Largest eigenvalue of Laplacian, as far as I know, does not carry a specific physical meaning. Yeah, so it is the smallest one that has some interest, smallest and the next smallest. Okay, so now I will give you 4 examples why these eigenvalues are important in a real situation. Okay, so for example, this let us say this Kuramoto model. I am sure this must have been introduced already here at some point. Okay, so which is about the dynamics of phases like this. Okay. Omega n is frequency which is taken from some distribution, plus you have you sum over this, and I have some function of theta m minus theta n, and typically there is a parameter k here. So, in the standard Kuramoto model, so this is taken from a distribution, typically a symmetric distribution. Okay. So, there is a distribution associated with this omega n. So, in the standard Kuramoto scenario, there is a critical value k less than kc, okay, for which the oscillators are incoherent. And for k, the parameter k greater than kc, the oscillators become coherent. Now, if we slightly modify this model and put in a network, put it on an arbitrary network.
What is incoherent?
Incoherent simply means that there is some order parameter which takes a specific value. Okay. So, you can say that the oscillators are in phase, okay, or maintain a particular phase difference, a constant phase difference. So, whereas incoherent means that they will not maintain a phase difference. So, in this case they would maintain. So, you can think of it as going from not synchronized to a synchronized scenario. Phases are synchronized.
So what is that f of?
So, it is some function of in the standard Kuramoto model, this is simply a sine function.
Sir, how network behaves as oscillator?
Huh?
How that network behaves as oscillator?
How network, no, network does not behave as an oscillator. On the network you put oscillator at every node of the network, and then they are coupled to each other. So, now you can actually add an arbitrary network effect by simply putting in a AMN here. Maybe I should put that here. So, this is a modification that is done to the Kuromoto model. So, this brings in the adjacency matrix here, AMN. So, in this case again I am not going to do this in detail, but just to tell you that in this case this shows a transition, this system transition from incoherence to coherence, or you can think of it as asynchrony to synchrony. Yeah.
How do we get AC value?
Okay, so one way is normally you define what is called an order parameter, no? Something which will define for you the order parameter will take different value in this phase and different value in this phase. Okay. And one way is the simplest way of doing is numerically compute that order parameter as a function of this k. So, when you do that it will stay at let us say 0 here in this regime and will go towards maybe some non-zero value in this regime.
AC can't be solved from the error equation.
For the simplest case of Kuromoto model it can be solved, yeah. But I am not sure that it is solvable when you put in an arbitrary network. Which? Yeah, that is right, it tells you which nodes are connected. So, you actually have an arbitrary network, on each of them you have a Kuromoto model and each one connects arbitrarily to few other nodes. So, in other words each node is a phase oscillator and each of them will have its own intrinsic frequency. So, yeah.
Why it has come from a distribution?
Okay, if you do not take it from a distribution, it is not a very interesting case. That is a simple problem that is solved in many textbooks. So, the Kuromoto model you have to take it from a distribution. Okay, so here once you put in this network, you will see this transition from this state to this state. So, in other words basically it is like saying that I have some order parameter which characterizes these states and here is k as a function of k, maybe it is 0 somewhere here and then goes up like this, becomes non-zero, something like this. Okay. So, roughly somewhere here could be Kc where it goes from 0 and becomes non-zero. So, in this case it turns out that this Kc, the critical value at which it transits from this property to this property is actually given by K0 by lambda 1, okay, where lambda 1 is the largest eigenvalue of A. So, you see that it actually is an important quantity that you need to worry about, these eigenvalues. Okay. They define what is, yeah. So, K0 is simply the Kc here. So, in the standard Kuromoto case. So, in other words if the critical parameter value is K0 in the standard Kuromoto model, once you put in the network effect, Kc becomes K0 by lambda 1, that is the change that it brings. So, here the network effect enters this critical value through lambda 1. So, if you want to see more of this, you should read this paper. So, another example I want to give is of diffusion on graphs. So this is example 1, if you like. This is second one. So I assume that this graph has n vertices, and typically you can think of it as maybe random walkers on a graph, okay, on a network, and this x is a vector. So this is the governing equation. So there are many diffusion processes. Simplest way to think about it is like you have a network, and maybe you are starting with large number of walkers or even a single walker at some particular node of the network, and that walker will keep randomly exploring the network. So what is the dynamics? How would we describe the dynamics? So this is the governing equation. L is the Laplacian matrix, and x is a vector that tells you the state of each vertex. Let us say that if like this is my some arbitrary network that I have, something like this, you can say that I am putting in some w random walkers at this point at initial time, and these walkers are going to simply explore this network, and this one has 1 2 3, there are 6 vertices, and this x vector will simply be like x1 x2 up to x6. So if let us say at some particular time there is only one walker at this node, let us say this is x3 for example, this is the third node, and in which case this x3 will be equal to 1. So it simply tells you what is the state of the node as far as the walkers are concerned, and this one can be solved. So you can write it as e power minus LT. So this is your initial distribution of walkers over this network, and you are asking what is the distribution at some other time. So you keep solving this at particular time, you will get this. The thing is that remember that this L is a matrix, not a number. So you need to compute exponential of a matrix. So again I am not going to do that. There are easy techniques to compute exponential of a matrix, but for now, for what we need, this let us say the initial distribution, I can write it as sum over C alpha V alpha, where this V alpha are the eigenvectors of Laplacian, or the eigenvectors of this Laplacian matrix. Okay. So in other words, I am using the fact that LV is equal to lambda mu V. So now if you substitute this back in this equation, so it will be e power minus LT acting on this C0 V0 plus C1 V1 and so on up to maybe Cn Vn. Okay. Now this one is so these C's are all coefficients, because this initial distribution you can always expand in terms of the eigenvectors of the Laplacian. That is what I have used here. Because you are working in the same space, any distribution in the same space can be expanded in terms of these orthogonal eigenvectors. Yeah. So that's the state of each node. So if you have 6 node like this is actually a vector x1, x2 up to x6. So state of each node, let us say in the context of random walker, could just be how many walkers are there in each node, okay, in the simplest case. And this one, for example, it's very easy to deal with that. E power minus, so if I have something like this, e power minus LT acting on C0 V0, this can be written as e power minus L acting on, this is a number, you can take it out, L acting on this eigenvector will give you mu 0 times T times C0 V0. C are expansion coefficients. So, this C, they are all expansion coefficients which you do not know at this stage. You do not know what they are, but in principle you can find out if you want to. Yeah. But the important point is that, so now I am operating this only on this term, which will give me this, but the smallest eigenvalue of a Laplacian is 0, as I said, which means that this mu 0 is actually 0, which means this will not exist, which will give me simply C0 V0. So now I can rewrite this as T is C0 V0 plus e power minus mu 2 into T times C1 V1 plus and so on. Here, that is because mu 0 is 0. No, that is what? Mu 0 is 0, because the smallest eigenvalue of the Laplacian is 0, I just told, right?
Yeah, but that equation, e to the power minus LT C0 will be equal to that one.
Yeah, so when you put mu 0 equal to 0, this simply becomes 1. So I think in I had erased that part. So when I described the Laplacian, I said that the smallest eigenvalue is 0.
No, explanation. Look above.
From here to here. Oh, how did I get this one? Okay. Okay, so you need to use this. So again, see, when you have structure, okay, let me explain this in case you are not familiar with the way it works. So you can take this C0 outside. So this I can write it as C0 times e power minus LT times V0. This is a number, so forget it. Now this one is actually an operator, it's actually a matrix. L is a matrix and exponential of a matrix is another matrix. So it's a matrix acting on a vector here, V0 is a vector, okay. And so I will not prove this, but this L acting on V0 will give you this one, okay. So L acting on the first eigenvector will give you mu 0 times V0, or L acting on V1 will give you mu 1 V1 and so on. So you simply use that property, so that this will give you C0 times e power minus mu 0 T times V0. Huh? Yeah, you can actually do a Taylor expansion of this operator, formal expansion, then term by term you have to use this to do the operation and then do a resummation. So if you understand this, you can try, but otherwise go back, look up books and try and do it yourself. Okay, so now we have this one, so you can keep doing this, but let's just keep these two terms, okay. So now this one is actually time independent, okay, it's some stationary state, So this one actually tells you at what rate you are actually reaching this stationary state. Okay. So in other words, if I identify this mu2, remember mu2 is the eigenvalue of the Laplacian matrix, I can identify this, I can give it a kind of name, call it TD, which is a diffusion time, and that is simply 1 divided by mu2. So in which case this term here, maybe let me write it here. So this times so yeah, so this actually tells you, it defines for you this time scale, which is called the diffusion time scale or mixing time scale. So this tells you how long it takes to reach the stationary state. Yeah. Mu1, I am using mu0, so this should be mu1. Yeah, and I should use the same thing here. Okay, here it doesn't have. Yeah, mu1. Yeah. So the point of doing all this is to tell you that for dynamics on a for dynamics on a network, the second eigenvalue, first eigenvalue controls the stationary state, second eigenvalue tells you how fast you are reaching that stationary state. See, I mean, to give you a very physical example, suppose let us say there are no air currents here, no AC is operating and so on. I leave a scent bottle here and just let it open. After some time you will see that the scent bottle, the scent is kind of there everywhere in the room. How long does it take for it to mix completely and be there everywhere? So that is your stationary state. Okay. So which means that you won't have a situation where the scent is selectively can be felt only in one point and not in some other point, assuming very ideal conditions. Okay. So in that case there is a drift and things like that, but diffusion is a process which doesn't have any directional preference. In all the directions it spreads out uniformly. Okay. So if I open the scent bottle here, maybe these are the people who will get the smell of the scent first, those who are in the last row will take some more time. So that is the mixing time, that kind of time scale, and that time scale, if you think of it in terms of network, is defined in terms of the second eigenvalue of your Laplacian.
Network has some disconnected component.
Hmm.
Still can it reach to a network?
No, it cannot. So in all these cases you assume that the network is, every node on the network is reachable from every other node. So if you have two disconnected components, you can't reach. So yeah, it's like an equilibrium state which is time independent. Yeah.
Also, that has to be used.
Sorry. Yeah. Mu.
So I think when you initially defined the eigenvalues with the Laplacian, the ordering was the other way around.
Other way, is it? Okay, sorry, I kind of keep, okay, so here at least, irrespective of how I think there I defined mu n as the smallest eigenvalue. So here I am taking this to be the smallest eigenvalue. This mu 0 is the smallest eigenvalue which is equal to 0.
Also, when you got the following made destroyed, why x3
No, I just gave that as an example. It's not one. It could be anything. I just said that if there is one walker on this, an example of what numbers you will put in here would be that. Okay, so I have given two examples as to why the leading eigenvectors are important. So I think if I have two more examples, but if I continue this, I think I will exhaust my time. So let me go to something else. Okay, so maybe I will state, I wanted to state many things without proof, but I will just state one thing without proof here. So for example, if you have a large network, in general, large network, which means n is much greater than 1. Okay. So in that case, you can ask, how does the largest eigenvalue of adjacency matrix increase with the mean degree of the network? So again, all these can be shown analytically, but I am not going to do that. I will just tell you that for the case of, say, one dimensional lattice, it simply increases linearly, and even for the case of Erdos-Renyi network, you know what is Erdos-Renyi network, right? Yeah, a random network. So lambda 1 as a function of mean k increases linearly. So this is the largest eigenvalue of the adjacency matrix, and for the case of say this a scale free network, it generally has a square root behavior like this.
Sir, what is the first case?
It's just a linear lattice. Let's say you connect the nearest neighbor nodes.
How can the mean degree vary in a linear network?
No, you are varying the this one the number of connections. Like you can have a case where you only connect nearest neighbors, or you connect nearest neighbor and the next nearest neighbor and keep doing that. Okay, so now what I have done is till now told you why this largest eigenvalue is important, or the smallest eigenvalue of Laplacian matrix. Why is it important? It appears in this kinds of dynamics problems on network, or it helps you study some structural properties of network, whether it is connected or not connected and so on. Now basically till now we have simply looked at this extremal eigenvalue, the top or the smallest one, but what about the bulk of the eigenvalues? If your network is has n vertices or n nodes, then there should be other n minus 1 or n minus 2 eigenvalues. They are called the bulk of the eigenvalues. What can we say about them? So what can we say about Shakti? I have to stop at 11. Little bit. Okay, fine. Okay, so typically this is what happens. Let me first show you what happens through a graph. So if I plot the real part of the eigenvalues, so now for this graph I am actually looking at the adjacency matrix which is directed. So the eigenvalues are complex numbers, they have a real part and an imaginary part. So if I plot the real part versus the imaginary part of
eigenvalues, what you will typically see is that there is one large eigenvalue, which is what you call the lambda max or lambda 1, whichever way you want to call it. So, here I have called lambda max as lambda 1, and rest of the eigenvalues are typically clustered around here. So, this one is an outlier and it is guaranteed to be a real number from what is called the Perron-Frobenius theorem. So, I will not prove this. Basically it says that if, let us say, you have an arbitrary matrix which has all non-negative numbers as entries, okay. All the n by n entries are non-negative numbers. In that case, it says that the largest eigenvalue of such a matrix is guaranteed to be real and non-zero. Huh? It should have been along this one, right? No, imaginary value is 0. Yeah, that is okay. It's a real number, so imaginary value is 0. All the rest of the eigenvalues are going to be here. So, this is what you will see if you actually take any Erdas-Renyi graph, compute the eigenvalues, take a large ER graph. You can do it as a simple exercise, numerically compute all the eigenvalues and just plot the real versus imaginary eigenvalues. So, you will see this structure. There is one that is an outlier and everything else basically becomes a cloud of eigenvalues. And same thing repeats itself even if you do it for a scale free network. In fact, I do not even have to draw the figure again, it is exactly the same figure. So, this is also valid for a scale free network. Take a scale free network, maybe a preferential attachment algorithm or something, or a configuration model, and compute all the eigenvalues and plot the real versus the imaginary eigenvalues. You will see one that stands out and rest of it is clustered in a cloud. Yeah. Yeah. So, here it is directed because otherwise you will not get real and imaginary. Actually, the story is same even if it was undirected. You will always have one eigenvalue which is dominant, which is away from rest of the crowd, even if you take an undirected network. So, this basically implies that if you have one eigenvalue which stands out from the crowd, it implies that you have one community or one cluster in your network. You can have a situation where it is not one eigenvalue, but maybe you have two eigenvalues which are standing out from the crowd. In that case, together these two things basically tell you that there are two clusters in your network. So, you can verify all this. The easy way to verify is take some simple scale free model with two community structures and compute the eigenvalues and see whether you are getting two eigenvalues which are away from the cluster. And in general, if you have, let us say, NC is the number of clusters in your network, then you will have NC eigenvalues which are outside the bulk, I mean outside this cloud of eigenvalues. In that case, yes, it will be real. Perron-Frobenius theorem only says about the dominant eigenvalue. It does not say that the second eigenvalue should not be real. Okay. So, it does not preclude that possibility. Okay. Now maybe it is a good time to start with. So, there are many other properties of this which for example, you can show that the size of this cloud, typically it is like approximately it is like a circle. The size of that the radius of that cloud is of the order of the mean degree of your network. So, there are many such properties you can show, but let us say for example, if you had more than one cluster and if the sizes of the clusters are all the same, then these eigenvalues will merge into will be degenerate, meaning that they will be same eigenvalue. And if the size of the cluster each one is different, if you have 4 clusters and each size of the cluster is different, then you will have 4 separated eigenvalues. So, there are many such properties. Since I am running out of time, I will probably skip that. A good place to read about these is this paper. So, now we can ask what about how do we describe these bulk of these eigenvalues. Okay. So, one way to describe them is, so like you are given, it is like you have been given n eigenvalues, n numbers basically. In that case, what would you do with those n numbers? One way is you ask for what is the distribution of those n numbers. You will calculate some statistical quantities building upon those n numbers. So, one way is you ask for the distribution of those, and that is called the spectral density. So, this is the spectral density is denoted by rho of lambda. This is simply the number of eigenvalues in the interval between lambda and lambda plus d lambda. So, in other words, you have your eigenvalue axis. Let us say this is my eigenvalue axis. So, to simplify, to get an understanding of this, you can for the moment assume that the eigenvalues are all real coming from an undirected network, and this is my eigenvalue axis, and the eigenvalues are going to be something like this, distributed over this. Okay. So, now we are asking the question, I define some this is lambda and this is lambda plus d lambda, and this width is d lambda. We are asking the question how many eigenvalues will lie in this. Now, this is a question that is asked quite a lot. If you are a physics student, you will relate to this question. This is what is called the density of states.
Isn't lambda itself the eigenvalue?
Yeah, lambda itself is the eigenvalue. No, lambda itself is the eigenvalue. So, this is the eigenvalue axis. So, meaning that see it can go from minus infinity to plus infinity, but in that axis there are specific points at which the eigenvalues of your given network is located. Right. So, it is like you have a set of numbers, n numbers, and you just put a point along that axis. Yeah, that is all. And you are asking, like, if I take a small interval, how many eigenvalues are there in that interval. So, I will just finish this one just by giving you an intuitive feeling for what this quantity is about. So, for example, again if you are a physics student, you must have seen that if you have a harmonic oscillator potential, even if you are not a physics student, you probably know that this famous formula that En is n plus half h bar omega. Energy is some quantum number plus half times h bar omega. So, what is important for us is not this formula, but these values are located equidistant from one another. Now, if you ask the same question in some given interval, how many eigenvalues are there? It will be same everywhere, because it goes from 0 all the way to infinity, n equal to 0 to infinity. It does not matter how high in the spectrum you go and ask the same question, you will have exactly the same number of eigenvalues, because it is equidistant. But on the other hand, if you remember your hydrogen atom problem, the potential, effective potential will look like this. This is the 0 in the energy scale. Here you will have energy eigenvalues which are distributed like this. As you keep going up, the spacing decreases. So, finally it becomes like a continuum here. There are very, very close energy eigenvalues. Now, you ask the same question in a given energy interval, how many such levels are there? Actually, it increases as you go up, whereas here in this case it was a constant. It does not go up, does not decrease, it is the same. Whereas here, as you go up the energy axis, there is a crowding effect. The more and more eigenvalues or energy crowd the same given interval that you choose. Okay. So, that basically is quantified by this eigenvalue density. It tells you how crowded is your interval. Okay. Yeah. And this is where if I try to take any network and compute the eigenvalues and then plot, let us say for this ER network, you will get what is called a semicircle. So, this is rho of lambda as a function of lambda. So, you take a large Erdős-Rényi network, compute its eigenvalues and plot the distribution or the spectral density. It will look like this with some fluctuations around it, but roughly it will be a semicircle like this. So, it will be like this. Now, where does this is called the semicircle formula or Wigner's semicircle formula. Where does this come from? So, this Wigner's semicircle formula actually comes from random matrix theory. Okay. So, just to close this session, I will just draw one more graph of spectral density for a scale free network, which will look almost like a triangle, something like this. It is not a semicircle. So, it is a semicircle and coincides with the random matrix result of Wigner's semicircle only for ER network. For a scale free network, your semicircle will look like this, but the actual reality, if you take a scale free network, compute its eigenvalues, it will fall on this curve, what looks like approximately a triangle. Okay, so now rest of the work is we will see where now random matrix theory comes into the picture, and now we will see how we can make use of random matrix theory from here on. We will start that in the next session. There are some questions people are asking.
What is it mean to, what does it imply as?
Yeah, so this is basically tells you like suppose let us say that the question that we are asking is what is the kind of interaction in your graph, in your network. So, if you are given a large graph, you can say, okay, I know everything about the graph, let me examine one by one and understand. Okay, that is one tedious way of doing it. Other way is, can I compute some gross quantities and from that say something about what kind of interactions are there and so on. So, these are a series of such measures. Spectral density is one of them, there is spacing distribution and so on. There are a whole series of such measures which help you understand kind of randomness that is embedded in your network. So, we have already dismissed the case where we were only looking at the first and maybe the second eigenvalue. That is one aspect of the problem. tells you something specific about maybe a diffusion time scale or something about the algebraic connectivity in your network. So here now the information you are going to get is not about such is more about the gross information of how is information kind of embedded in your network as.
So you mentioned that it's lambda max would be like the outlier.
Yeah.
So here you see that
In real networks, yeah, there are outliers, which means that they basically it's basically a signature that there are some correlations, which is not described by random matrix theory. Yeah.
So at lambda max, do we have rho lambda max in it? Because it's separated from the.
Yeah, so what you will typically see when you actually do with even real network is you will see some eigenvalue which is outside this semicircle. Those will be your lambda max. So there will be a small bump here, or sometimes more than one bump.
So no density there, like. Density.
Yeah, this is low density, but it's important because it contains some useful information. So this being described by random matrix theory basically means that there are random correlations. So what is lying outside of it has something that is non-random, which is probably useful for you. So that's the idea behind using random matrix. So you describe what is uncorrelated or what is random, put them all in one basket. Anything that stands out of that is what is possibly that you may want to examine closely. Yeah.
So here you're taking the absolute value.
Huh?
Here you're taking the absolute value.
No, so here I am assuming a very simple situation where it is undirected network, so eigenvalues are all real. Yeah, I mean, when the eigenvalues are complex, the formulas get much more complicated. It's not easy. You can't just take the modulus and do this analysis. It won't follow this.
so if I take just a prediction, it will not give me the.
It may or may not give you the thing. At least there's no theory saying that you will get that.
Is there a reason for the distribution?
This one? Yeah, it is symmetric. Okay, I'll think about it. I don't have an immediate answer to this.
Similarly, in the scale-free network, is it like symmetric about 0?
Yeah, generally it is symmetric about 0. Yeah, there may be some. See, there is no. I mean, to a first look, it is symmetric. There is no clear way of. The semicircle has a definite formula and it is symmetric. Whether your real network is symmetric or not is a different question, but the semicircle formula as given by Wigner is symmetric. Whereas here there is no such analytical formula, so you can't say whether it is strictly symmetric or not.
It might have a long tail in one.
It may have, yeah, all that is possible, and when you just look at it to a first approximation, it looks symmetric. Yeah.
Can you try to like explain why there is this triangular peak by just preferential attachment?
Yeah, so generally this kind of peak is associated with what are called localized eigenvectors. That means that in your scale-free networks, there are these collection of nodes which work in tandem. So they make their presence here roughly in this region. All the eigenvalues in this region at the top essentially come from that collection of nodes which contribute strongly to a particular eigenvector, which means that they have something important to tell you as far as the network is concerned. This kind of analysis does not tell you what is that information it's trying to tell you. It just says that there is something that's not quite random and yeah. So the eigenvectors associated with the peak are typically localized. The ones associated with these are typically delocalized. We'll see at the end of the course, if I have time, I'll at least devote 5 minutes to this localization.
Okay, so with that,